After we've run all of these models, we want to find a way to be able to evaluate if these are good models or not. And we'll introduce here a few different calculations that try and tell us whether the model was good or not. But there are other ones as well, so you could find other ways to evaluate the models. I'm going to use some of the most common, and then you could think about other ones if you're interested. Here I'm going to start with the r squared, and I'm just using the formula for the r squared. There are other ways to do this in packages that are available, but I think it's worth knowing how to calculate it. And here I'm taking the training data. So let's start first with what we had last time. So with this linear model, I created a fitted column and a predicted column. So these use this model that I estimated, and I'll run it right now, and then create a fitted value and a predicted value. So the fitted is for the training set, the predicted is for the testing set, and now we can use these fitted values and predicted values to then go evaluate if they're any good. So the formula for r squared, that's what all of this is just the formula for r squared. It's in the slides, but it is the observed value. So here I'm using the training data set, and I'm using the y variable that I want to predict. And we have observations where we see what the variable is we would predict. Of course, if you're going to make a prediction, let's say for next year, actual next year from our current calendar time, then we don't know what that is, and so we wouldn't be able to evaluate it until after time has passed. But here we have data where we have looked at what that is, and here the training data, of course we have it because that's how we set up the model. But the formula is the sum of squared residuals, that's this top part, divided by the total sum of squares, and then 1 minus that is the r squared value. So here, revenue growth minus the fitted value, and we square that. That's this first part, and then sum it up. And then the bottom part is the total sum of squares, which is revenue growth, the thing we're trying to predict, minus the average revenue growth, and square that. So in other words, the comparison is if we only use the average, then how does our model compare to only using the mean? Okay, so we run this. This should be between 0 and 100%. And notice it's the same as what we got in one of the regressions. It's 7%, and that's the training data set, so seems okay. We can also do the exact same thing on the testing data set. What is different here is that this is the predicted value rather than the fitted value. So this is the predicted r squared. So all of this now is the testing data set and the predicted value, but the rest is the exact same equation. So we run this. Well, what happened? So we had 7% on the training data. Our model didn't work quite as well. We moved to the testing data, and we've gone down to rounded 6%. This is something that typically happens, right? Models are fit on data, and of course, the model is set up to capture the variation that is in the data that it's trained on. So it's always going to work better. Well, not always, but we expect it to work well on the training data, and often if it fits some weird oddities in the training data, it won't fit quite as well on the testing data. Of course, the ideal situation is we get really close to the same sort of ability when we move to different data sets, that we predict just as well or close to just as well when we move to a testing data set. That's the goal. We don't want to do any worse than we would, from the training data. Of course, some of these models that we have can do a lot worse because we do what is called overfitting training data, and so it does a great job of explaining all the weird things in the training data, but does poorly when we get out of sample. That's the big issue, so we will look at that as well. So, okay, so there's another approach that we want to look at, and this is the mean absolute error. And absolute error means how far on average were you away from the actual result versus what you predicted. So we could run this here. So this is just the absolute value of the difference between the thing you're trying to predict and what the model predict. Run that. So the average of that difference is 27%. By 27%, I mean that 27% is the percent growth in revenue. That's the Y variable. So we're 27% off on average. That's not fantastic, right? We would like to be really close to what the prediction is. Of course, that's just a reflection of the fairly low R squared. For comparison, this 27%, how much you're off? Well, let's just look at what the average revenue growth actually is. Well, the average is 13%. So on average, we're way above and way below this. If we do the mean absolute revenue growth, you will see that that's pretty much the same as what the error we're getting. So our model is almost the same as just assuming that you have zero revenue growth in the future. And we could also look at the full distribution. How far off are we? So do this mean absolute error again. And the median is 11%, 12%, and the mean is 27%. So on average, we're quite a bit off. There are some down here where we're really close. We're near, we're almost right on at the minimum. The first quartile, we're only 5% off. We have some out here where we're really wrong at the maximum, so not fantastic, but it gives us an idea about how that model works. I want to give one more possibility, and this one introduces a few code items here that hopefully is useful. And this is introducing logical operators, so is it true or false? And each one of these is a piece of a logical operator. So this first one says, is revenue growth next year positive, greater than 0? In parentheses here, this will return a true or false because it's a logical operator. So yes, it's greater than 0, then that's true. If you took away these parentheses around these things, they would get confused. So first then, let's say this is true, so it returns true here. Then in this one, it says the fitted value, that's the thing that the model predicts. So if that's also positive, then the first one is true, the second one is true. Double equal signs means is equal to. So this is another logical operator. So if true is equal to true, then it's going to return true for this first piece. Or if either one of those is not true, then it will return a false. This vertical line is the OR operator, so it says this first part or this second part. So if they're both positive or they're both negative, so the same logic occurs. This is true or false, this is true or false, and then this bigger parentheses will return a true or false because either they're both positive or they're both negative. If either one of those happens, this whole thing will return a true value. If neither of those happens, meaning this ends up evaluating to false and this evaluates to false, then this whole thing will be false. Well, that's for each individual row. So then we can take the average of those. How it works in R is if you average or do some statistics on true or false, it'll turn it to ones and zeros. Because 1 is true, 0 is false, then it gives you the percent of observations that are true. So let's run this. On average then, how often do we get the sign right? Meaning when it actually is positive, we say it should be positive, or our model says it should be positive. When it actually is negative, does our model say it is negative? We run this. Well, at least in the signs, we get 65% of the signs correct. So we can be more confident that when we say it's going to be positive, it actually is positive, and when we say it's going to be negative, it actually is negative. Not perfect, but it at least gives us something to work with. Well, we can repeat these exact same tests, these R-squareds, mean absolute errors, and correct signs for every model that we've used. So I'm just going to do a couple of these. So because these linear ones I named the same, I said I was going to change them, I'll just leave them the same. but I have to run them again. So now this EST is my polynomial model. I can run this same thing. Now notice I'm doing the prediction with the training data set. That leads me to the fitted value. So I can run this. And for now, I'm just going to do the R squared, but all of these are the same thing as we had before. So notice the R squared is 7.9%. So we've got the same R squared as we get from the model. That's because it's the training data. And for fun, do we get better at this at all? We get 64% where we're correct. Before it was 64%, so basically the same. We can do the same thing with the interaction model. So run this. And we have the same R squared we saw before, and it's probably not going to matter much. 64%, rounded 65%. So not too much help on any of these. So now let's go to these other ones. If you still have it here, you don't have to run it again. So we can predict for the random forest one. So we run this, calculate the R squared. So now notice instead of 7% R squared, we're up to 80% R squared. That sounds great, right? On the training data, that means that the random forest model does a great job of capturing a lot of the variation in the training data. The big question will be when we go to out of sample, does it work at all? But let's try these other ones. So the absolute error, 12%, that's much better. And the getting the signs right, now we're up to 90% getting the signs correct. Sounds good, right? Okay, so we're moving in the right direction, but this is, again, just the training data. The real question will be when we move to out of sample. So let's look at some other stuff. I wanted to point out here, we could change some of our models and give different parameters. So for example, if we wanted to adjust the random forest, so my note here was when I ran it before, it ran for about an hour. I'm not going to run that now, but I just want to explain some of the controls. So we already had a seed set. You know, we could change that seed or do the same thing. Since it was 5, whatever I used before, I'll just leave it in there. But one of the parameters you can do is tell it to do different control functions. So here, training control. And this train control, what it tells it is how to use the training data to check and make sure it's coming up with good parameters for the model. So this is, again, sort of deeper machine learning stuff, but this repeated cross-validation, this is saying use 10 folds and repeat it 5 times, and it's going to search over a bunch of parameters that you're going to input. And what we could do is change this here. So you have to look up and see what the parameters are that go into each model. So here in the random forest one of the parameters that you can adjust is this mtry. So mtry is how many random variables do you input when you're calculating the random forest. So we can run this. It turns out when I ran this, it works just as well with the 1, which is the default, so that doesn't matter very much. So anyway, so we can notice here we've got this tune grid. That's this thing that we've set up to run over different parameters, and the training control is this part. So we can use it in some of the other ones where it actually does matter. So then the next question is, how does it work when we move to out of sample? So if it works well in sample, that's great, but if it doesn't work out of sample, then that sort of defeats the purpose of the thing we're trying to achieve. So here I'm going to do the random forest, apply it to the testing data set, and do the R squared value. So sort of same thing. We could do the same thing with how often we get the prediction right. So one of the things that random forest or any of the forest methods are notorious for is overfitting training data, meaning they look really good on the training data, you move to testing data, and it sort of falls apart. So if you are enthralled and excited at this point, when you hit run, you can anticipate what you think it's going to be, and based on prior stuff that people have done, it won't be as good. So we run this. Notice we're at 6%. So basically, we're in the same situation as if we use the linear model. So not quite as good. Part of that can be because we used the default here, this default training control. Actually, if you allow it to have more folds and more repeats of the cross-validation, it does slightly better, so we can get up above this 6%. So it's not great, but it's slightly better than we had with the linear model. But the big part that I want you to focus on here is the in sample and the out of sample are quite different. So let's try the XGBoost. We can do the same thing. Again, I'm using this training XGB object we had, and we can look at the R squared. So in sample, we get 13%. So it's not nearly as high as the random forest, which we saw overfit the data. Let's look at how often we get it right. 65%, so we're basically the same as if we were using the linear model. So let's look at something you can do for the XGBoost package and that model. So same thing here, we're going to use this bigger number, more repeats, and we're going to use the grid function. We already have the seed set, so I'm not going to do that again. And if you want to understand what it is, you can go to this website and you can find all of the things that go into the training and the parameters that can be there for training the model. So we can adjust this a bunch, and each of these things needs to be in there. And if you don't have the right things in there, it'll bring an error to tell you that's the case. But number of rounds is the number of trees to consider. So I'm going to do 10, 50, and 200. The depth is how deep the trees will go. So I'm going to do 3 levels, 5 levels, and 10 levels. These others are parameters to limit overfitting. So that can help. And then these are how much to use of the data when you're going through all these sampling rounds. So again, this is the tune grid. We have this control set up here. And other than that, all the rest is the same in the training function. So we're going to use this tuning grid, meaning go through all these things and then use the controls that we set up. So you could run this with all of these parameters, train it, and you could adjust these parameters and try different things. Of course, the more complex you make it, the longer it takes to run. And when I ran this particular setup, it took about 10 minutes. I have this set up so that if you wanted to do it and run through it and compare them, you could. What I want to focus on more importantly is this next part, and this is the XGBoost run that we had of that, and we're going to apply it to the testing data. So we're going to look out of sample, how does this work? So we go ahead and run this and then look at the R squared, and you see it had the best in sample R squared, and we move to out of sample, we're up to almost 11%. So this model, the XGBoost model that we have so far, is the best model both in sample. Well, in sample it's not better than the random forest, but random forest seems to really overfit, so the XGBoost seems to be working quite well, and it's better out of sample. And it's better than the linear models as well out of sample. This is comforting at least a little bit because XGBoost in a lot of competitions ends up being one of the winners, at least over the past few years. So the last one, neural net version. So we run this. It can take a little while. It's not super long. We ran it before, so you could run this. But then we want to look and see how did that do in sample. So we go ahead and run that. And 12%, notice that's kind of like the XGBoost model, and that is consistent with one of the other winning models, ends up being some of these various neural network models. For fun, does it get the sign right? We're about the same as before. So a little bit better prediction. Now the question is, does that work out of sample? We could test all of those things as well. And then again, if we wanted to look at other possible things for trying the neural network on different types of controls, well, there are different parameters that we need for neural network models. You can look these up again. Here it is 2 different parameters. Size is how complicated to make the neural network model, so bigger numbers is more complicated, and decay is how much to reduce overfitting, or at least the attempt to reduce overfitting. And so then you could run this as well, and it takes a little while because this version is not too long. It wouldn't take too long to do it. So again, we could look and check and see. I've left these things in here for you to check and see how they're doing. But then let's check out of sample with the one we've already run. And it's 11%, so let's go ahead and look back at the XGBoost was 10.5% in the testing data. The neural network was 11% in the testing data. So really with all of these things we've looked at, the ones that seem to work the best for our data and the parameters we've chosen. So of course we could adjust these parameters. So what you haven't seen then is what if we do more training here with different parameters? Does that improve it even a little bit more so our new neural network model works even a little bit better? That's possible. Same thing with our XGBoost model. The big question then is with how long it takes to run and it's not super intuitive, is 11% versus the 7 to 9%. Are we better off using the neural network or the extreme gradient boosting models, or are we almost as good the other way? That leads into a whole bunch more evaluation that we might want to do. So main points that I want you to get out of this are we have some ways to evaluate whether the models work well in sample or out of sample, and there can be some extreme overfitting. So that's one of the big reasons so much effort goes into training, is to try and figure out, can we fit things without overfitting them? All right, it's a lot to learn, a lot to work on. What I don't want you to do is get too bogged down in the details of how these models work, but I want to present them so that you can have the opportunity to work on them, if that's something you're interested in, and we could continue on that path a little bit longer.